All right, welcome back, guys. So, spring 2024, lecture day 4. We're covering recursion. With Professor Hat. So let's get some include shit going on. Let's get our using namespace std. Let's get an int main void running. The return 0. Bam. All right, let me come steal all those things we're going to use. All right, we'll shoot them down as we're going. And we'll start with bool is prime. Okay, so we are covering recursion. Recursive functions do function calls to themselves. So they're like this bool function or this is prime function. When we go through it, notice that it says return is prime with something different. So it's returning is prime, but this is different than like P and I equals 2. This is starting with something different. So it wants to do something different each time. And so it must keep going until it hits a stopping point. So recursive functions make functions calls to themselves. And if designed properly, we'll have a base case where there's a return that isn't a function call to itself. In this case, we have 2 of them right here. Return 1 or return 0. If we're checking prime numbers, let's just take a look at what this function is doing. Let's run it. Let's run is prime. See out. We want to send in a P. So like, I don't know, 111. And an integer I. What the hell is the way this thing working? Okay. Oh, we don't need to provide another thing. We can just say is prime. Is prime 111. And let's just see if it runs. It says 0, which is probably a terrible way to say this. So maybe we'll do assign an integer real quick. In x equals 111. That's something we'll change. We'll do a cout is x prime. And then we will have, let's set up a Boolean y equals is prime x. Make this nice and neat test case. If y equals 0, that's the no case. We will see out is not prime. And then else, see out is prime. I hate this shit at the top and the bottom where it's right on the edge of the screen. So I'm gonna address that real quick. I'll smooth this up here. We have our declarations at the top. All right, so we're just seeing how this works. So it says it's not prime. We know 19 is prime. Let's give that one a try. Is prime. Okay, so this thing works. Let's take a look at how it's working. Let's go with the smaller prime we know works. X equals 7 is a prime number, and it'll be a shorter way of showing this recursive call. So let's come take a look at the function. And I'm going to write this down and put it on the document camera real quick. Actually, I don't need to. I can have my both up at the same time. So we are doing, I did top. We set in is prime 7. So what's going on here? It sends 7 over into memory, and we've got P. What it's taking into memory is the P, so that's 7. So it's taking in, it's got P equals 7, and I defaults to 2 at the base that when it starts. And now it says if I equals P, return 1. It does not. If P mod I equals 0, like if I can divide P by 2, return 0, because then it's divisible by 2. It's not prime. If it directly equals it, like if P equals 2, it starts off prime. If it doesn't, what happens? This is going to return is prime 7, and then I plus 3, or I plus 1 would be 3. What I'm doing right now is called a recursive trace. This is very fucking handy when you're trying to figure out what's going on, and it will be on your exam. We'll do this on paper in class. Okay, so practice this. There's a problem in the worksheet or in the labs that has you practice it. So we're looking, and then so, okay, what do we got here for the next case of this? P equals 7, I equals 3. Does 7 equal 3? Or mod equals 0? No. So we have to return is prime again. is prime 7 comma 4. And again, 7 does not equal 4, and 7 divided by 4 does not have a remainder of 0. So that's the modulus part. And it's not evenly divisible, and it doesn't equal it. So again, we're doing return is prime 7 comma 5. We're trying to return it, but we haven't calculated is prime 7 comma 3 yet. And is prime 7 comma 3 is trying to calculate is prime 7 comma 4. This one's trying to calculate 7 comma 5. These are programs that are building up in memory. This is called the recursive stack. Other teachers like to show it going upward. But like if you're drawing it by fucking hand, who starts at the bottom of the fucking page? And you never know how much room you're going to need, so you don't want to start like in the middle of the page. It's easy to do the stack. We're having a stack go downward, even though normally when you stack shit up, you're just piling shit on top. And the same thing is happening visually here, except we're going the other way. We're stacking things on the bottom. So we're constantly lifting up the stack and putting shit underneath. 7 comma 5. We've got p equals 7, I equals 5. Again, 7 divided by 5, or 7 mod 5, I should say, does not equal 0. And 7 doesn't equal 5, so we're going to return 7 and then, or is prime 7, and then I plus 1 is 6. We've got p equals 7, I equals 6. That doesn't work. Return is prime 7 comma 7. Equals 7, I equals 7. And now we finally hit this line. If I equals p, return 1. Do you have another color? All right, so this 1, that is the is prime 7 comma 7. So this is going in right here. So this now says return 1. Because is prime equals 7. Or is prime 7 comma 7 equal 1. This returns 1. Well, this was is prime 7 comma 6. So this comes up here, and this is the value 1. So this now says return 1. And as each of these returns it, the function, the program's completed, it pops off the memory. Here, we got to return 1, so we're going to return the 1. We got a 1 here. This closes off. We return 1. Put a 1 here. This closes off. We return 1. This closes off. We return 1. That equals 1. And then we had our C out. We have y equals 0. It's not prime. And since that doesn't fall under that case, we fall under it is prime. This is called a recursive stack. Normally it goes the other way. So you can kind of see like 7 comma 2, 7 comma 3, 7 comma 4, 7 comma 5, 7 comma 6, 7,7. That's why they call it a stack. It keeps going up, 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 up. Finally gets to a case, the base case, where it did equal. So it returns a 1, 1. And they call this popping off the stack. This is a stack in memory. And eventually get down to the 1. And we return the 1 to the program. Or to the main. Or wherever we called it. With each one getting waxed or erased as it goes. This ultimately will work faster than doing a non-recursive approach. So I'm going to point that out here. Recursive functions are usually faster than, they're called iterative functions. That's where you go through a for loop until you get to where you need to go. They come at the cost of memory. Or that speed comes at the cost of temporary memory. Which means, depending on how much memory the computer has that's running this, it sets a cap to how big of a number I can check. Let's test that. X equals 7. Let's change it to, I don't know, 500. Wait. That's going to hit it. That's divisible by 2 right away. That's going to return that. Let's see. I need a really large prime number. Is 501 prime? There were build errors. What happened? Well, I need to know why I have a build error. What fucking changed? Let me go back to 7. What? I might have fucking went too big already. I might have so much of my memory. Nope. So what did I fucking break? We're not doing Fibonacci yet. Int P equals 2. All I did was type this fucking bit right here. That ran. It was literally my fucking. What's wrong with this? Oh, there it goes. Okay. Whatever was there was fucking up. What am I trying? Oh, crash. Stack Overflow. I've exceeded the amount that my memory can to allot to this. I prefer iterative because it's easier to set up. If I really need something that goes fast, then I'll take the time to do it. But like, I'm not a programmer, I'm a teacher. So like, I haven't had to choose one yet. So this was 7. What was it? Fuck off already. Stop. There you go. Whatever I picked, 7,841 was too big for my computer memory. Now, if you have enough memory, it might be good for you, but fucking add enough digits and your shit's gonna crash eventually. Even supercomputers are gonna fucking run out of memory if you pick a prime number big enough. Right. So we could write this as an iterative one. Yeah, bool. Let's call it iterative prime. And it takes in P. How will we do this? Well, I said we could do a for loop. Let's kind of like steal what it's got going on there. Ni equals 2. I less than or equal to P. I plus plus. And fuck, I can literally just copy and paste that shit. Fucking stupid. They sell these things, these document cameras, but the stand and everything that comes with isn't large enough that you can get the whole paper. Even if you fucking have it pointed straight fucking up and that fucking make a bigger stand, jackasses. I literally at home, I have the box it came in as my fucking stand, which is lame. All right. I'm assuming everyone had a chance to do that. We're gonna come down here and try that. So I will comment out that. What? Let's find out. Equals iter prime 7 or x. Right? All right, that's all we've changed. And now let's see if my shit will run. Oh, someone's chatting here. Alex says his shit went through. And this time it did go through. So the iterative model will go through because it's not doing this. It's just doing one call and it's fucking keep writing over the same fucking area doing the check. Now, I don't know why this one, these two, one would be faster than the other. But there's got to be some setups where it's definitely one's got a better payout. Let's take a look at another one. The Fibonacci sequence. You all know the Fibonacci sequence? If you don't, and maybe I shouldn't assume everyone does. It's exactly what happens. So the Fibonacci sequence, it starts with 2 1s. And then each number after that is the sum of the 2 previous numbers. So 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 3 is 5. 3 plus 5 is 8. 13, 21, 34, 55, and it keeps going. That's the Fibonacci sequence. So it's the sum of I minus 2 plus I minus 1, basically. Or I should say xi minus 2 and xi minus 1. Because not necessarily I, it's the x term, xi term. Let's come over here and run back. In fact, you can see that there is the sum of x minus 1 and x minus 2. Sending those in. So let's check out using the Fibonacci sequence. Let's see. Well, we could go, this one's fucking bitch. This one's a bitch to draw a recursive or the recursive stack for it. So let's go low. Let's start with 7. And then we'll go bool z equals what is it called? Fibonacci x. Maybe we'll come down here and we'll say something similar, but with the Fibonacci sequence. So maybe I'll put in a little, it's a little bit easier to find this shit later on. So is x a Fibonacci number? And we'll change this to x is a Fibonacci number. Or is not a Fibonacci number. And it is a Fibonacci number. And all I gotta do is change this if loop to z now. So we just showed the Fibonacci number. 7 was not one of them. Let's confirm that what I've got listed here is doing what I think it is. Seven, what? It says it is. So, is it doing something different than I think it is? Where is it? If x is less than 2, return x. So on the Fibonacci sequence, if x is less than 2 is your base cases, the ones that are just base part of it. Otherwise, return Fibonacci x minus 1 plus x plus 2. Oh, wait. Is this producing that number, the Fibonacci number? Let me go through and change this to 4. And I'm going to comment out this shit right here. I don't think it's doing what I think it's doing. See out Z. The 4th Fibonacci number is 3. The 4th Fibonacci number is 3. So if it's doing that, then running this is going to say 3. It says 1. What's going on here? Let's figure it out. Let's do a recursive trace. It's returning a 1. Did the 7 return a 1? Let me check the 7. The 7 returning 1. Oh, I've got it doing a bool. No. Let's change Z to an integer. That's the problem. Let me see out Z again. 13. which was 1, 2, 3, 4, 5, 6, 7. The seventh Fibonacci number. And that's what we were looking at. I had in here. So it is returning which Fibonacci number it is. It's yeah. So a better C out here would be the blank Fibonacci number is, nope, that's X. X was the input and the output is Z. Now this is going to look funny if we put a 3. So we could set it up, but that's a better way. That's always good. All right, so let's do the recursive trace on it for 7. How did it get to 13? That might be pretty big. Fuck it. Let's do it. Let's come over to the camera. Let me make sure the Fibonacci sequences, our code is on the camera. Because we're here, we're learning how to do these Fibonacci, these recursive traces. All right, so we start off and we're saying we sent in Fibonacci 7. That's the function call we did. So we're sending in X equals 7. It says if X is less than 2, return X. Otherwise, return fib I minus or X minus 1 plus fib X minus 2. In this case, that is fib 6 and fib 5. So this will be fib 6 box. And this will be fib 5 box. So X equals 6 here. 6 is not less than 2. So this is returning, I'm just going to say ret fib 5 plus fib 4. Well, we got fib 5 written over here. So I'm going to point over to it as well. And then we're going to make fib 4. And I'll write fib 5 real quick. Fib 5, we got 5, and it's going to return fib 4 and fib 3. Yeah, it's adding the 2 before it. So this one needs fib 4, and it needs fib 3. Watching Redden do this, he fucking makes this giant fucking tree, rather than reusing. And that's really what's going on. These are two, fib 5 here and fib 5 here are 2 different function calls. It's going to show up twice in memory. So this is our first fib 5 call. So that's going to be higher or lower in the stack near the bottom. And this was our second fib 5. So it's a little bit higher. But they're both happening. It's not pointing to the same memory thing. Even though I'm doing that to save paper, I want to make that crystal clear. It's like branching out. It's going to do fib 5 twice.
there a reason why it's pretty much almost like
I don't know. Yeah, but why is the golden rule pure nature? Some would argue proof of God, intelligent design, yeah. Or it could just be fucking chance. Like, it might be a tricky question to think, why are most celestial bodies almost spherical? You would wonder that until you go, wait a second, I know how fucking gravity works. And it fucking never pulls everything in, and eventually it's gonna fucking make it so, like, if it's too high on one side, eventually there's gonna be some erosion. Anything happens, it's gonna push it over and make it a sphere. But until we know why, it's just magic. So fib 3, x equals 3, is gonna return fib 2 plus fib 1. And fib 4 does fib 3 plus fib 2. So fib 3 is, this is pointing over there. Again, two different fib 3 calls. And fib 2, this one's doing fib 2. So fib 2 is 2. Is x less than 2? No. 2 is not less than 2. So this one's actually going to return fib 1 plus fib 1. So we'll call this fib 1. And rather than drawing it twice, I'm going to show it, pointing to it. These are two different spots on the mound, the stack. This shit's building up with shit that's going on. And 1 is less than 2, so it's going to return 1. So, back arrow. This sends 1 back. This sends 1 back. This sends 1 back. We get to here. This is 1 plus 1 equals 2. This sends a 2 back. And fib 2 is over here, so it's sending a 2 over there as well. And now we've got both parts here. This is 2 plus 1 equals 3. That's sending a 3 there, and it's sending a 3 there. And I've got both of these. This is 3 plus 2 equals 5. So the fourth Fibonacci number is 5. Oh, wait, let's look at this. Let's put that son bitch back down here where we can see it. Why is it saying the fourth Fibonacci number is 5? That's not right. Am I missing something? Oh, this is doing fib 1 plus fib 0. My bad. So that is not return. So it's this is that's not pointing to that one again. This is pointing to fib 0, which is less than 2, so it's returning 0. So this is actually getting a 0 back there, and this is 1 plus 0 is 1. That's sending a 1 there and a 1 there. This is a 1 plus 1 is 2. Look at me just. I'm glad I fucking looked. I wanted to say, look, the fourth Fibonacci number is 5, and it's not. And I did fucking help me catch my error. That's fucking handy. This is, so that's a 2. Let me just cross those off and fucking write them better. That's a 1. That's a 1. All right, so here we've got 1 plus 2 equals 3. So we're returning a 3 there, and we're returning a 3 there. And the fourth Fibonacci number is a 3. Excellent. We're on track. So we've got fib 4 plus fib 3. Fib 4 was 3, and fib 3 was 2. 3 plus 2 is 5. So our fifth Fibonacci number is 5. And it's returning a 5 up there. And it's returning a 5 up there. Remember, these are all different stacks. Even though I've got them listed twice or once, each back arrow is indicating a different stack. So this one is pulling in fib 5, which is 5, plus fib 4, which is 3, so that's 8. So the sixth Fibonacci number is 8. Confirmed. That's sending back an 8 there. And here we're getting 8 plus 5 equals 13. And so we get back here, C out 13. That is how that shit works. It's a recursive trace. Yeah. I don't know. I'll have to get back to you on that. I'll find out why. For loops take more time. For loops, it's a longer, like doing something iterative, like the amount of time spent per each operation.
Oh, okay, so maybe because the like the math is a lot more basic.
Right. This is just one input, one output, and it's doing math here. It's doing math here, whereas if we do the for loop, we still got to do the if thing on every single search. This is where it is, the iteration part. We're kind of doing the same thing. In an iterative loop, we're going to have to do this kind of check each time. But the for loop, incrementing and doing all of the is for int I equals 2, I less than n. Each of those checks, you got to check if I is less than n. That adds a little bit of fucking time to it, where we don't have that check here. We're just doing the math. So they both do the math, but the for loop has the little micro fucking cosm of time to also check if I is less than n.
And in exchange, though, you have to be you can't just
Right.
say, "Oh, that's easy."
Right. Well,
It's just saying that for the
it is not fucking simple to write.
Just like have enough practice, it's really simple. I guess I don't know, but it says that it's fast when you look at the reason it's faster is because apparently recursion follows more function has more function calls inside. It causes it to go slower because
Maybe on the Fibonacci sequence, because each one is splitting and doing 2, whereas in the for loop, it's not doing that.
There's also like the charts that if you look at them, some of them maybe in the beginning it's really like slow, but the more calculations you have to do slowly. So it might
Huh. Generally, for bigger things, it's supposed to be better with recursion for speed, but you pay for it in with memory. Because otherwise, we would never use recursion. Because it definitely eats up fucking more memory. So why would they ever do this if it didn't have the fucking speed element? And it might just be the Fibonacci, since it does 2 different calls inside. That might be slowing it down. Where it's, I don't know. If you picked a high enough fucking number, you could have the computer time it. But I think I'd blow up my fucking memory pretty fucking quick. Because each number splits into 2 more numbers. Because really, what's going on here? I drew mine nice and neat. But this is doing 7. 7 goes to 6 and 5. 6 goes to 5 and 4. 5 goes to 4, 3. 4 goes to 3 and 2. 3 goes to 2 and 1. This goes to 2 and 1. This goes to 1 and 1. 1 and 0. This goes to 1 and 0. This one actually does the return. It goes back. This one goes to 1 and 0. So even though I just drew Fibonacci 2 once, look at all the fucking, like this is, each one of these is a generation of the fucking a Fibonacci thing. So like each of these numbers is running the program once in the memory. And I just did the fucking 5 there. Or the 6. 6 isn't even finished. This 5 thing would duplicate over here. But then we also have the 3 and 2 in here. 2 and 1 in here. 1 and 0 here. 1 and 0 here. So all of these are going on. Even though I made it look nice and tidy up here, this is doing a lot of fucking function calls. And each one's not done until it gets down to the fucking 1 or 0. And then it starts giving information back upwards. So you can see how that would eat up memory fucking pretty fast. Because the 7th Fibonacci number is not asking for a fucking big number. To get to 13, fuck it. We're going to write it out. Because I really want you to see how many fucking circles there are here. 2 and 1. That goes to 1 and 0. No, I want to see it. I don't trust me. You should never fucking trust me. I don't know what the fuck I'm talking about. There we go. That's all the fucking calls it did. You will see me write like some shit in a math class that says like 2 + 2 is 6. You can't fucking always trust the teacher. We make mistakes. But if you recognize a mistake, you better fucking call us on it. Usually the mistake is us thinking ahead and like 6. If I said 2 + 2 = 6, 6 is showing up somewhere later. It might even be in the next fucking problem. Because I got lecture notes sitting next to me. Or, I don't know, got distracted. Whatever the case is, we make mistakes. So that's the Fibonacci sequence. Can we write this iteratively? Let's take a look at writing it iteratively. How do we do this? A for loop or a while? I'm going to say, I'm going to call it fib number. I'll just use fib there. Fib equals, I don't know, 0. Maybe a counter. Do a counter. I'll do a int counter. That makes sense. For we're doing a counter. I'm going to call it counter. Int count equals 0. Count less than X. Count plus plus. I should be using I, but in my head, even though I is a counter as well. And I need a tally thing. So let's just make a temporary integer sum equals 0. We'll initialize it. And we'll do this. We'll do I need and x1 equals 1, and x2 equals 1. So how are we going to do this? No, I'm going to start with 0 on one of them. This will work. So I'm going to say sum equals x1 plus x0 or x2. And then I'm going to say x1 equals x2. X2 equals x. Wait, I need to do something else here. So the sum is like the current total. So like it might be 8. Let's look at this one like this is like 3 and 5. Let's say this is 3 and let's say this is 5 real quick. This can help us think about what we're doing here. Like how would we set this up? You should do sum plus plus. That should just be adding 1 to the sum.
But if we say that x1, x3, and x2 is 5, would it sum plus plus it out? Or would it,
Sum plus equals. Oh, it depends on how you, okay. So the first go around, right away, it does 1 count, and sum is now going to equal 1. And then yeah, I think I could use some in here. Because that's like the new number. Sum is the new number. And then I'm going to say x1 equals x2, and x2 equals sum. So this would make sum equal 8. And then this is going to say, that's going to set this one to 5. And that's going to set this one to 8 for the next call. And then the next call would be sum is 13. I think that'll work. I think. There's got to be more than one way to do this. So int z2 equals iterfib x. And we just saw this one eats up a lot of fucking real estate. So I'm going to call that one off. And I'm just going to come down here and say the z2 here. Now we should still get 13 if my iterative function worked right. MFR. I just broke the shit. What? Like I don't even want to fuck close. I broke the internet. I don't even want to fucking close. MF. Come on, close. With what? Task manager, yeah. There we go. I win. Right? I beat the system. All right. So where did I piss it off? Close that shit down. Oh, I don't have it returning anything. Fucking scrub. Oh, too far. So what if I start count at one? There we go. Let me confirm it. Let's do the 9th Fibonacci number. Or the 10th. I wrote out the 10 on paper. The 10th Fibonacci number was 55. There we go. What? It was going too many steps. Any questions? Do we want to try to take a look at this other one? Binary search. So we send in an array. We send in a first number, a last number, and a target number. So we're searching for a number in the array. And we're trying to return the index or what position in the array the number is found at. Well, I think what's going on here, let's just draw an array real quick. Here's my picture. Fuck, did it fucking kill visualizer too? It fucking did. I broke my fucking computer. Okay, first off, change the orientation and change resolution. Bring our code back up, bring this back up. Fuck. This is what I wanted to move. Why can't I move it? Fucking changed. It doesn't have the visualizer's a bitch. It gets fucking all moody and it makes it so I can't even move it anymore. All right. So let's write an array here. What's going on? Let's just take a look. Let's make it a fucking short array. 1, 3, 5. I was gonna do all odd numbers, but let's fucking change it up. And let's say we're searching for 3. And we're taking in a first and we're taking in a last. I don't know what these are yet, but it says if first is greater than last. So this is assuming they're in numerical order. Because if they're not in order, eventually something's not going to be correct. It says mid, we'll call it mid. Mid equals first plus last minus first divided by 2. Is this like the positions in the array? Or is this just actual values? Like, let's say this is 1 and 10. Let's see what would happen. This is saying 1 plus 10 minus 1 divided by 2. And these are integers, so this is doing integer division. So this is doing 9 divided by 2 is 4 in integer division. And would say mid is 5. And it's going to say index equals mid. And now it's saying mid is an index. So I don't think first and last are the numbers in there. First, this should be where in the fucking array we're looking. So this should be 5 minus 1 would be 4 divided by 2. 1 plus 2 is 3. So this is doing mid. I know I'm not on screen anymore. Let's bring that back up. Mid equals 3 and going, if target equals array 3, maybe mid should be 0. It should be 0 and 4. 0 plus 3 minus 1 is 1. What else is it? It's a weird code. And we're doing it because that's 0, 1, 2, 3, and 4 position. What is going on here? Let's say the target equals 8. Let's go for 8. Because I don't want it to be the first one we find. If it's this, then 4 minus 1 is 3. 3 divided by 2, and integer division is 1. And this would be a 1. So mid equals 1. And then it's checking, does target equal array 1, which is 3? No. Is target less than 3? That's the else if. No. You're right. Thank you. So this was the if. This was the else if. And we finally get down to else. And else is do binary search. Do the call again. Send in the array. Send in. It's got to be mid plus 1. Mid plus 1, last, and target. So mid plus 1 would be 2. Last would be, I reset this to 0 and 4. 4. And target is 8. And then it does it again. Mid equals, first is now considered 2. So 2 plus 4 minus 2 divided by 1 is 3. So now it wants to check, is target equal to array 3? Is 8 equal to 8? Yes. So it's going to return 3. I think that's how it's working. Let's try it. Let's set up this array and see if that's what's going on. Come down here. And we're going to do, what is this called? Binary search. Binary search takes in the array. This was all wrong. I'll just get rid of that. So we'll do a cout binary search. And we're sending an array. We're sending in 0 and 4, and we're going to send in the target number 8. And it should tell us it's in 3rd position. Yeah. So that is what it's doing. So if I was trying to do the recursive trace on this, doing 8 here, it would have been, all right, we've got binary search, array, 0, 4, 8. And what does that do? We've got arrays in there, and it says first I'll call f equals 0, l equals 4, and it calculates mid to equal 1. And what it returns is what I showed here. I'm going to just say bin search to make it a little shorter. Array 2, 4, 8. So we come down here. This is a short recursive trace because there's only 2 steps. I guess target still needs to be listed. Should list that up here. Target equals 8. And so now it calculates mid to equal 3. And that was the target. So it returned 3. So it sends 3 up here. Pops that bad boy off the stack. This is 3. That's what's returning. It sends 3 here. Pops it off the stack. And we have a cout of 3 here. I deliberately chose a short fucking array, so it should take that long to fucking search. Because we had 15 minutes, and I fucking managed to do that. Figure it out. Now, we were going to go over later in this class, setting up iterative searches and doing shit like that. There's a lot of ways to do searches. So we got a whole module later on in doing it. So I'm not going to bother with an iterative model right now. This is how recursive trace works. Good stuff. FNL's Friday, 6 o'clock. There's gonna be a great announcement there. I know what the announcement is, but I can't tell you until FNL. Yeah. Yeah. We're gonna, as soon as 7:15, we'll play around doing the monster thing that we were talking about the other day. And you don't have to leave. Juan's here till another 2 hours if you guys got questions on anything. Other than that, peace out. Any questions from the folks online? Oh, I see Juan and Hefe in my picture. You ruined it. Yes, sir. Well, we're not gonna make a whole game. Yeah, we're designing classes and that do inheritance. We're just playing around with stuff that we learned. What? We're gonna do a little of each. Got template is always the last thing you kind of do.
I used like something else. I didn't use RPG character.
No shit. You want to send this to me? And I'll go through it, look at it at home.
Yeah.
That way I'm not making you sit here, watch me play on your computer.
So
Because if it's a good thing, we'll start with that tomorrow and add to it, if you don't mind.